Welcome to the next part of our lecture on Chapter 5. We're now going to look at Section 5.6, which is defining sequences recursively. A recurrence relation is actually something we've already gotten a sneak peek at with some of our induction proofs. Now, a recurrence relation is any sequence which can be defined by the previous terms. So when you are relying on the next term being defined by what happens before it. Some famous sequences which are recursive are Fibonacci, amongst some others, and we'll talk more about the Fibonacci sequence a little bit later. So we said that that's any sequence where the next term is defined by previous terms. It doesn't matter how many previous terms you're looking at. It could be one, it could be 100 previous terms. However, the next term must be defined by the previous term or terms. Okay. One other specification here is that you must be given initial values. So if you're defining something off of one previous term, you have to know at a minimum what any of those previous terms might be. So the catch is that initial conditions must be given, or initial values of your sequence. Let's look at an example here. Find the next three terms of the sequence for c sub k. So they've given us here, for all integers k greater than or equal to 2, c sub k is defined by the k minus first term, which is the one that comes directly before it, and k times the k minus second term, which is 2 before it, plus 1, with c0 equals 1 and c1 equals 2. So let's just list those out there so they're a little clearer. So c0 is 1, c1 is 2. If we want to find the next term, so now let's look at C2. According to this formula, that's going to be 2 minus 1 is C1 plus K is 2 times C2 minus 2 is 0. And we know both C1 and C2 as those were our initial values, initial conditions, if you will. So by plugging in, we have 1 plus, sorry, that is 2 plus 1 times, sorry, let's try this one more time. So by plugging in here, we get C1, which is 2, plus 2 in this case because it is C2, so it's 2 times C0, which is 1. Let's see, that is 2 plus 2, which is 4. So we've just found that C2 is equal to 4. If we want the next term, C3, that's going to equal C2 plus 3 C1. Again, both of which values we know. C2 is equal to 4 plus 3 times C1 is 2. 4 plus 6 is 10, and so on and so forth. So let's just do one more to have this completely filled in. C4 is C3 plus 4C2. So we have here 10 plus, again, this is the previous term, 10 plus 4 times 4. 10 plus 16 is 26. So then these would be our next values. And you can continue this on and on. Now, recurrence relations are a blessing and a burden at the same time. They're a blessing because you don't need to know a whole lot. You just need to know what the previous terms are. But they're a burden for the same reason. Like in this example, if we wanted to know what C100 is, that means that we would need to know C99 and C98. Whereas if you had an explicit formula, that would be dandy. You could very easily just plug in and get your 100th term or whatever you need there. So we're going to talk about what happens when we are dealing with recurrences and how we can approach them. Let's look at an example. Construct a recurrence relation for a compound interest question. So if you're familiar with compound interest from a different course, set that formula aside for a moment. We're going to talk about how we can generate a formula for this relation and then how they're very similar to what your fancy formula would be. Suppose a person deposits $100 into a savings account at 7% interest compounded annually. So note that they're saying annually here, that just means one time a year. What is the initial principal P naught? So the initial value is what we're plugging in here, which is $100. So if we are opening this savings account, we're putting $100 in. What is P1? Well, if it compounds annually, that means at the end of that first year, I get 7% of interest. So P1 is whatever I had at the start, which is P0 plus 7% of it, which a shortcut to this would be combine like terms. This is 1 plus 0.07 is 1.07 P0. And in this case, since we know that amount, 1.07 times 100 is $107. So at the end of that first year, we have $107. Now, we can keep going on, and our goal here is to find a general formula. Well, without going too crazy, what does P2 equal? Well, P2, we're saying now at the end of 2 years, we're making the assumption no money has been taken out or put into this account. At the end of the second year, we're gaining another 7% on top of that money that we already earned. So why is it compounding? It's compounding because we gain that money and then we can earn interest on the new amount. And we said, well, it's going to be the year before it, which is P1, plus 7% of interest. On top of that, oh, hey, look, that's again 1.07 P1. But hey, we knew what P1 was. P1 is 1.07 times P0. So if we keep substituting in here, we're going to notice a formula starts to emerge. Well, how many 1.07s do we have? We have two of them. So if we have two of those values, we can write that as to the second power. 1.07 to the second times P0. Now the cool thing about this is if you leave it with the P0 in there, no matter what your initial value is, this formula will always work. Now if we repeat this for P3, what do you think is going to happen? We're going to have that same exact thing continue to appear. So if we wanted to find a formula for this, let's say P sub n equals 1.07 to however many years we've compounded for, because in this case we're compounding annually, times P0. So our general formula for this exact case would be P sub n equals 1.07 to the n times 100, since that was our initial value. If instead you're compounding annually at 7% and you plugged in and you started with, let's say, $1,200, again, then you would just replace the P0 with 1,200. So this is pretty cool because it's very general, no matter what type of amount you're investing to begin with. Now, based on what we learned in our previous sections on induction, we can definitely prove that this formula works. So we can look into that at a later time.